Hello, everybody. So today we are going to go through our stoichiometry gizmo simulation, and hopefully this will help us understand stoichiometry more, a little bit more reason behind why we set up the numbers the particular way inside of our train tracks. So before we get into our simulation, we're going to be doing a few prior knowledge questions and a little bit of a warm up. So part of this simulation handout is going to be just us and the questions on the handout. The other half is actually using the Gizmo simulation. So I figure that walking us through this first section and a little bit of the second section would help us out. So let's get into it. All right, our prior knowledge question number one. If we have a 250 milliliter glass of orange juice containing 22 grams of sugar, how much sugar would be in a 2-liter bottle of orange juice? 2 liters is the same thing as 2,000 milliliters. Now, you might do this calculation a little bit differently normally, but since we are in chemistry and we have learned about dimensional analysis, let's set it up our dimensional analysis way. So 2,000 milliliters over 1. And then since this is milliliters, we've got to bring that down here. And then we're wanting grams of sugar. So that goes up top. And then we're going to be using these numbers that they gave us as our conversion factor. So 250 milliliters under 22 grams. When you put this into the calculator, you're going to take 2,000 milliliters and then multiply that times 22. And then whatever you get from that gets divided by 250. And so your answer is going to be 176 grams of sugar. All right, let's do a little bit more practice. Number 2, it requires 2 sticks of butter to make a batch of 20 cookies. How much butter will it take to make 150 cookies? Well, our given is 150 cookies over 1. And then, according to the first sentence, for every 20 cookies, we're going to use 2 sticks of butter. So for this calculation, you're multiplying 150 times 2 and then dividing that by 20. So we're going to end up using 15 sticks of butter. And so that's our answer for number 2. Now for the gizmo warm-up, just talking through it. So kind of similar to the stoichiometry sandwich activity that we did a while back. This gizmo is looking at, or at least these 2 questions, are looking at how a cook uses a recipe, kind of like how a chemist uses stoichiometry to figure out the amounts of substances involved in a chemical reaction. So we're going to try our hand at figuring out the amounts of reactants and products that take part in a chemical reaction using our stoichiometry gizmo. So to start, we got to check that this equation is what's shown in our simulation. So if you signed up for an account using my classroom code, then you should be seeing something similar to this. You've got stoichiometry listed here, but we want to click the button that has the rocket ship where it says launch. And that's going to launch our gizmo simulation. And lo and behold, we've got our equation that we're wanting to show here. So we're good there. If it's not showing, please make sure to click the new equation button until you have the same equation that I have here. But before we start working with that, we got to look at the handout. So number 1, look at the coefficients, big numbers in front, of each substance in the equation. The coefficients are going to tell you how many molecules or atoms take part in a chemical reaction. So in these spaces, we're going to put those coefficients in, and that represents the number of atoms. So Fe2O3 doesn't have anything in front of it, but we always assume that's a 1 for that blank. In front of CO, we've got 3, Fe has 2, and CO2 has 3. So that's number 1. For number 2, to double check that this is a balanced equation, we're going to count the number of atoms on the reactant side up here, and then the product side down here. And as long as they are the same number, then that is going to be a balanced equation. So for iron, this subscript 2 means we've got 2 irons. Over here on the right side, since we've got a coefficient of 2, that means 2 irons. So that's the same. For oxygen, we've got 3 here, but also the coefficient 3 multiplies times 1. 3 plus 3 is 6. Over here, 3 times 2 is 6. And then for the carbons, 3 times 1 is 3, and 3 times 1 is 3. So since the numbers match on top and on bottom, this means that, yes, this is a balanced equation. So now that we've finished up the pre-lab, let's turn to the next page, activity A. So we're not quite using the gizmo just yet, but make sure that the equation is still this. If not, make sure to click new equation until it appears. Okay, so for activity A, we're just going to do a brief recap of the mole. So in chemistry, the mole is defined as an amount of a substance that contains 6.02 times 10 to the 23rd particles of that substance. That number, as many of you should remember, is Avogadro's number. And that's special because this tells us the number of particles that has a mass in grams equal to the mass in universal mass units of a single particle of that substance. So to help us recap, we're going to do a little bit of calculations. So for number 1, molecular mass of a molecule is the sum of the masses of each atom in the molecule. And the unit for molecular mass is universal mass unit, or lowercase u. So we're given these masses, and these match up with what's in the periodic table for each of these elements. I'm not going to do all of these for you. You are going to have to do A and B by yourself, but I am going to go ahead and do C with you guys. So for C, it wants us to calculate the molecular mass of iron 3 oxide, also known as Fe2O3. So for iron, it's listed as having 55.85 U's, but in our formula, we've got the subscript 2 next to Fe. So that's going to be multiplied times 2. These steps should be very familiar or familiar sounding because we go through the same thing when we calculate molar mass. Anyway, for oxygen, it has a mass of 16.00, but according to the formula, we've got 3 for our subscript. So multiplying that times 3, when we do this entire calculation, we end up with 159.7 U's. All right, for number 2, we're going to take this information and just add on to it because a mole of substance has a mass in grams equal to the molecular mass. So one of the reasons why this was very familiar is because these are the same steps we take to calculate molar mass. It's just that instead of having U's, we change that to be grams instead. So whatever numbers you have from number 1, you're going to replace that unit of U with G. So for Fe2O3, we had 159.7, and instead of writing the letter U, we're using G for grams because this is going to be the molar mass. This is how many grams equals 1 mole of Fe2O3. So just double checking our answers in the gizmo. Let's look at that simulation. So according to this, 1 mole of Fe2O3 is equal to 159.7 grams of Fe2O3. So that's right. All right. And then for the rest of these, do them on your own. Now looking at number 3, I'll do water with you guys, but the rest, again, on your own. So we've got the masses of iron, carbon, and oxygen, and it's also giving us hydrogen here. So to calculate the molar mass of water, we got to take our hydrogen mass of 1.01. Since we've got a subscript of 2 here, this gets multiplied times 2. But we also have to add in the mass of our oxygen. So doing this calculation, we're going to end up with a molar mass of 18.02 grams. And that's how many grams equals 1 mole. We're going to move on to activity B. So canceling units. When we are doing dimensional analysis, we set up the units and substances to be stacked diagonally with each other. And this has to do with information appearing in the top or the numerator and the bottom or denominator for a fraction. If they're the same thing on top and bottom, then they can be canceled out. And same thing applies here with our dimensional analysis, because even though they're diagonal from each other, this is still technically on top, this is still on bottom. And so they will cancel each other out. And that's the whole point of dimensional analysis, canceling the unit until we're left with the unit we're wanting and the substance that we're wanting. So what we're going to do is now we're actually going to be using the simulation completely and totally. We're going to be following these steps, and we're going to be looking at the first question given to us that says how many moles of carbon monoxide are required to completely react with 1.75 moles of iron 3 oxide. And if this isn't the question that you're seeing on your simulation, click new question until it does appear. So looking at this first question, we can see that the unit given to us, and that's usually going to be the one that with numbers, is moles of Fe2O3. And what they're asking us to find is moles of CO. So then we're going to go over to our simulation, and we're going to find the tile that has moles of Fe2O3 on top and moles of CO on bottom, which is this one. And we're going to click and drag it down to that bar. Now, according to that tile, it has 3 moles of CO reacting with 1 mole of Fe2O3. So you'll want to write that number 3 in the blank for question 2. Then we're going to analyze this. To get the answer in moles of CO, we need to cancel the moles of Fe2O3. So we're going to click this checkbox that says Show Units, and we're going to write down the units listed on the right side of the equal sign for letter A, for number 3. But for letter B, these aren't the units that we're actually wanting according to 1B, and so we're going to click the button that says Click Tile. Now you're seeing that the moles of Fe2O3 cancel, leaving us with moles of CO. So that is now the given unit. So write that in for 3B. And then for number 4, we're going to calculate. We're going to multiply 1.75 times 3, and we should end up with 5.25 moles of CO. So that's what we're writing down for letter A. And then let's double check that. So show numerical result, and yes, we were correct. We have 5.25 moles of CO for our answer. So, very back page. These problems on the gizmo are in a random order, so you might have to click the new question button until you get the question that's being referred to. This is actually referring to question D at the very bottom. So we were going from grams of iron to molecules of carbon monoxide, and we had to use a lot more tiles to get to it, but we're still going to be canceling the units and following those tiles to get our final answer. Make sure to check both of these boxes so that you can get that answer. Okay, so That's it. You'll work on problems A through C and number 6 on your own.